We have seen many properties of the Laplace transforms, and we have also computed quite a few examples. Now we go back to the question of the existence of the Laplace transform. We have seen that functions which are piecewise continuous on the interval 0 to infinity with 0 included, and which are of exponential order, they have for them the Laplace transform exists. So this is a sufficient condition. Today we will look at the existence of Laplace transforms for functions which may not be piecewise continuous at the y equal to 0 line at the y-axis, and these functions are called functions with vertical asymptote at t equal to 0. And we will give a theorem which gives a sufficient condition for such a function which has a vertical asymptote at t equal to 0. For these functions, the existence of the Laplace transform is given, and using this theorem we can then compute the Laplace transforms of the functions t to the power alpha for alpha greater than -1, where alpha is any real number greater than -1. We have already computed it for any positive integer t to the power n, but this computation gives you the Laplace transform of t to the power alpha for alpha any real number alpha greater than -1. So today we will look at these things. So today we will continue our study for the problem of existence of Laplace transforms. We have already seen that for functions which are piecewise continuous, on the interval 0 infinity, 0 is included in this interval, and of exponential order, the Laplace transform exists. So this is the theorem we saw before. Today we will see conditions under which some functions which are not piecewise continuous, some functions which are not piecewise continuous on 0 infinity, conditions under which some functions which are not piecewise continuous on 0 infinity have Laplace transforms, meaning that their Laplace transforms exist. So let's review what we learnt about piecewise continuous functions. So our piecewise continuous functions on 0 to infinity, so this is the t axis, this is the y axis, and our piecewise continuous functions were broken up into chunks on some subintervals. So for every finite value r, this interval from 0 to r can be broken up into finitely many pieces, and this function ft will be continuous on each piece, and at the end points the left side limit and the right side limit are finite. So these are piecewise continuous functions on 0 to infinity. Here note that at 0, when we approach from the right, this limit is also finite. So it is piecewise continuous on the interval 0 to infinity with 0 included. Now we will encounter some functions which do not have a finite right hand limit when we approach 0 from the right hand side. It does not have a finite limit. So such functions are not piecewise continuous on the whole 0 to infinity, but we want them to be piecewise continuous for every interval when you remove 0 from the interval 0 to infinity and you take any small r here, then we want it to be piecewise continuous on towards the right, but as you approach 0 it will have a what we call a vertical asymptote. So what is a vertical asymptote? So vertical asymptote at t equal to 0. So we say that ft has a vertical asymptote at t equal to 0 if the limit t tends to 0 from the right ft does not exist. And is either plus infinity or minus infinity. So our picture now looks like this. So here's our t and y axis. Outside 0 it can have a piecewise continuous behavior, but when you approach 0, let's say it starts from here. When you approach 0, it will either go to plus infinity like this, or it could go to minus infinity like this. So here we have the negative y axis, and the function can have a minus, it can approach minus infinity when you approach 0 from the right. So this is 0, and when you are approaching 0 from the right, it either goes to plus infinity or minus infinity. So in this case, this line y equal to 0 is known as a vertical asymptote. So today we will see some sufficient condition under which functions which are piecewise continuous outside 0, but at 0 it has a vertical asymptote, may have Laplace transforms. So in this case we have the following theorem, which says that if ft has a vertical asymptote at t equal to 0, and if three other conditions are satisfied. The first is that ft is piecewise continuous at in every interval small r to capital R, endpoints included, where r is strictly positive and small r is strictly positive and capital R is greater than r, a finite number. The second one is what will interest us the most, which is that there exists a constant alpha between 0 and 1 such that the limit as t tends to 0 from the right side, t to the power alpha f of t equals 0, and the third is that ft is of exponential order. So the difference between this one and the previous theorem for the sufficient condition is that our function ft was piecewise continuous on 0 infinity, where 0 was included, but here 0 is not included and it has a vertical asymptote at t equal to 0. So it's not piecewise continuous for the interval 0 infinity where 0 is included, but nevertheless it is piecewise continuous from the first assumption. It is piecewise continuous on any interval small r to capital R. So it looks like our picture here, the second picture here, where it can go to either plus infinity or minus infinity as t approaches 0 from the right. But outside this t equal to 0 line, it is piecewise continuous and of exponential order, so it is well behaved outside this y equal to 0 line. So this theorem gives you a sufficient condition under which the Laplace transform of the function ft exists. So it's piecewise continuous on every interval outside 0, every finite interval outside 0. The limit t tends to 0 plus t to the alpha ft is 0, and the third is that ft is of exponential order. Then the Laplace transform exists. So let's see the proof for this theorem. First of all, we didn't define our improper Riemann integral in this case when the function is not piecewise continuous at 0, when it has a vertical asymptote at 0. So let's define what we mean by an improper integral in this case. Improper integral for functions with vertical asymptotes at t equal to 0. So in this case, the Laplace transform ft e to the power minus st dt, it has to be divided in two parts. So the first part is from r to some point a, ft e to the power minus st dt, and the second one is from a to capital R, ft e to the power minus st dt. Now note that we have to still take limits. So the second one will have limit as r goes to plus infinity, and the first one will have the limit as r goes to 0 from the right hand side. So here a is chosen. So this is a remark that a is chosen such that the function ft is piecewise continuous on a capital R and small r a. So our function needs to be well behaved outside 0, so therefore one can find such a point a, and this function will be now piecewise continuous on AR and a capital R and small r a. Now these two integrals inside the limits are ordinary Riemann integrals, and because the function is piecewise continuous, the Riemann integrals will exist, and then we take the limit as r goes to 0, small r goes to 0 from the right, and capital R goes to plus infinity for the second integral. So this is our definition of the Laplace transform in this case. So to prove our theorem, we need to show that this integral 0 to infinity ft e to the power minus st dt exists, meaning that both these limits in this definition exist and are finite. Okay, so let's see how it's done. It's a little bit tricky, so please pay careful attention. So first of all, we can write down the definition as is written above. E to the power minus st dt plus limit r tends to plus infinity a r ft e to the minus st dt. Now I am going to choose my a carefully. Choose the point A carefully so that the limits exist. So for this I will use the second part of the assumption, which says that the limit t goes to 0 plus t to the power alpha f of t equals 0. So this is by assumption 2. So we know that the limit as t tends to 0 plus, this limit goes to 0, which means that there exists an interval 0 less than t less than delta such that the modulus of t to the power alpha f of t is less than or equal to 1. So because the limit goes to 0, the modulus must be 1 for some interval 0 to delta. This is the definition of the limit. So now we have found this delta, and we will use this as our breaking point A in the definition of the improper integral. So we write our integral 0 to infinity ft e to the power minus st dt. This is equal to limit as r goes to 0 plus r to delta ft e to the power minus st dt plus limit r goes to plus infinity delta to capital R ft e to the power minus st dt. Okay. Now let's look separately at these two limits. So let's take the second one first. So let me call the first one I1 and let me call the second one I2. So for I2, we know that the function has exponential order. Ft has exponential order. So this is by assumption 3, and remember that it is sufficient to show that the limit as r tends to infinity, the integral from delta to r of the modulus of ft e to the power minus st dt exists. This is because absolutely integrable functions are integrable in the improper Riemann integral sense. So we have already seen this in one of the previous lectures, that it is enough to show that the absolute value of the function, when you take the integral with respect to the absolute value, then it exists. So to show this, remember that ft has exponential order, which means that our ft can be written we have an inequality for ft. So ft, modulus of ft is less than or equal to m e to the power alpha t for all t greater than or equal to some t naught, right? So we are going to break up this region again from delta to t naught and from t naught to r. So we can write I2 as the limit r tends to infinity integral delta to t naught modulus of ft. So this is not really I2 because I2 doesn't have the modulus of ft. So let me call it I2 prime. So this is I2 prime. So I2 prime, I am breaking up the integral inside the limit from delta to t naught and from t naught to r. So there is a e to the power minus st dt and then modulus of ft e to the power minus st dt. So now let's see what we can do about each of these integrals. First of all, because ft is piecewise continuous, on 0 infinity, modulus of ft is bounded on any interval alpha beta inside this bigger interval 0 to infinity. This is because it is piecewise continuous, so it cannot go to infinity in any of the interior points. So suppose that modulus of ft is less than or equal to some constant, let's call it c on, so this implies that modulus of ft is less than or equal to c on this interval delta to t naught. Okay, so then delta to t naught integral of modulus of ft e to the power minus st dt is this is less than or equal to c times integral delta to t naught e to the power minus st dt, which is nothing but c times c by s times e to the power minus s delta minus e to the power minus t naught, and this is finite, of course. So this first one is finite, and the limit as r goes to infinity is the same as this this value. So this is independent of r. So limit r goes to infinity does not change this value. Now for the second one, integral t naught to r modulus of ft e to the power minus st dt, I am going to use the fact that modulus of ft is bounded above by m times e to the power alpha t. So this is m times the integral from t naught to r e to the power minus s minus alpha times t, and this is nothing but m times e to the power minus s minus alpha times t naught minus e to the power s minus alpha times r upon s. So now we can take the limit as r tends to infinity on both sides, r tends to infinity. So we get here a limit and here a limit r tends to infinity is less than or equal to limit, well this is equal to limit r tends to infinity, and we see that the term containing r goes to 0 as r tends to infinity. So the limit is simply m times e to the power s minus alpha times t naught over s. So I2 prime, which is the sum of these two limits now, because both limits exist. So this is, the first one was from delta to t naught modulus of ft e to the power minus st dt, and the second was from t naught to r, the same thing, dt. This exists, meaning that this limit is finite. It is finite, and this implies that I2 itself exists because any absolutely integrable function is integrable. Now we still have to show that the integral I1, which is the limit near 0 as r goes to 0 plus of the integral from r to delta ft e to the power minus st dt exists. So this takes care of the vertical asymptote at 0. So what we will do is we will show that I1 prime, which is the same thing but with the absolute values inside the integral, absolute values ft e to the power minus st dt exists, and we will use the same argument that an absolutely integrable function, if it has an improper Riemann integral, then the original function itself has an improper Riemann integral. So now let us show that this limit as r goes to 0 plus of the integral from r to delta of the absolute value exists. So to show this, remember that for any positive r less than or equal to t less than or equal to delta, we had that modulus of ft is less than or equal to t to the power minus alpha. So therefore, in this region from r to delta, we have this inequality, and so we can write I1 prime as the limit as r goes to 0 plus integral r to delta t to the power minus alpha e to the power minus st dt. So it is enough to show that this limit exists. Now let us try to evaluate this integral r to delta t to the power minus alpha e to the power minus st. So here I will take u to be e to the power minus st and v to be t to the power minus alpha for an integration by parts formula. So we get t to the power minus alpha plus 1 by minus alpha plus 1 e to the power minus st from r to delta minus r to delta minus s. So differentiate u minus st and now integrate v. So t to the power minus alpha plus 1 over minus alpha plus 1 dt. This is what we get when we use the integration by parts formula. Now note that we had 0 less than alpha less than 1. So now we can simply write this out. So we will get delta to the power 1 minus alpha. So now this is a positive power of delta exponential minus s delta over 1 minus alpha minus exponential minus sr r to the power 1 minus alpha over 1 minus alpha. So this is the first term, and the second term we get s by 1 minus alpha integral r to delta t to the power 1 minus alpha exponential minus st dt. So now we would like to take the limits on both sides. So limit r tends to 0 plus r to delta t to the power minus alpha exponential minus st dt is equal to, so this first term does not have any r, this is a finite value, so the limit does not change this factor. So we have delta to the power 1 minus alpha e to the minus s delta by 1 minus alpha. The second term has r, so we have to take the limit as r tends to 0 plus r to the 1 minus alpha e to the minus sr over 1 minus alpha, and then again this third one we have to take the limit r to delta t to the power 1 minus alpha exponential minus st dt. So if you can prove that the limit in the second term and the limit in the third term exist, then this will mean that our I1 exists as well. So now it's simply a matter of seeing what are the two limits. So for the first term, we can easily show that the limit r tends to 0 plus r to the power 1 minus alpha e to the power minus sr over 1 minus alpha, this is simply 0. This is very easy to see because this is a continuous function and the limit as r goes to 0 plus is simply 0. And the second one, limit r goes to 0 plus integral r to delta t to the power 1 minus alpha e to the power minus st dt. This is simply Now the Riemann integration between 0 to delta of the function t to the power minus alpha e to the power minus st dt. We can do this because our integrand here t to the power 1 minus alpha e to the power minus st, this is a continuous function over the whole region 0 to delta. So we used that t to the power 1 minus alpha exponential minus st is a continuous function, is continuous on 0 delta included, 0 included. So therefore this limit as r goes to 0 plus exists and is equal to the Riemann integral. This is the Riemann integral in the ordinary sense. Therefore all our limits exist, and so I1 exists, and we have already shown that I2 exists, so therefore the Laplace transform exists.